Hello students, welcome to Physical Science Digital Classes Mahabubabad. Myself Narendra Babu PGT Chemistry TSMS Mahabubabad. Today, Atomic Structure Class 10 Part 4. In this session, we are going to discuss about quantum mechanical model of atom, quantum numbers. First, quantum mechanical model of an atom. Before going to see this, I have a question. Do the electrons follow defined paths around the nucleus? According to the Bohr's concept, electrons are revolving around the nucleus in fixed paths. This is the concept. My question, do the electrons follow defined paths around the nucleus? If the electron revolves around the nucleus in defined paths or orbits, the exact position of the electron at various times will be known. If the electron revolves around the nucleus in defined paths or orbits, the exact position of the electron at various times will be known. As per Bohr's theory, if the electron revolves around the nucleus in fixed paths or definite paths or orbits, the exact position of electron at various times will be known. Then again we have two questions. First question is, what is the velocity of the electron? So if we can able to find the position of the electron at various times, so position of the electron at various times, then what is the velocity of the electron? Second question, what is the exact position of the electron? But according to Heisenberg's uncertainty principle, it is impossible to determine simultaneously the exact position and the exact momentum of a subatomic particle like electron in an atom. What it is? It is impossible to determine simultaneously the exact position and the exact momentum of a subatomic particle like electron in an atom. Why? Why it is not possible? The reason is, to view any object, a light of shorter wavelength than its dimensions is to be focused on it, and the reflected beam of light should be observed. What it is? If we want to view any object, a light of shorter wavelength than its dimensions is to be focused on it, and the reflected beam of light should be observed. An electron is exactly smaller particle. A light of extremely shorter wavelength, that means higher energy, is required. An electron is an extremely smaller particle. That means a light of extremely shorter wavelength, that means high energy is required to view an electron. By absorbing this higher energy, the velocity of electron increases further, which automatically changes its position. Due to this, simultaneous determination of position and momentum of an electron cannot be done accurately. Electrons, by absorbing this higher energy, the velocity of electron increases further, and which automatically changes its position. As the velocity increases, then so its position will be changed. Due to this, simultaneous determination of position and momentum of an electron cannot be done accurately. With this, it is clear that electrons do not follow definite paths in an atom. And one more question. Do atoms have definite boundary as given in Bohr's model? Do atoms have definite boundary as given in Bohr's model? If electrons are not distributed in orbits around the nucleus, then an atom does not have a definite boundary. If electrons are not distributed in orbits around the nucleus, if the electrons are not distributed in orbits around the nucleus, then an atom does not have a definite boundary. So, it is not possible to find out the properties of an electron in an atom. Erwin Schrödinger was developed a quantum mechanical model of atom to understand the properties of electron in an atom. Erwin Schrödinger was developed a quantum mechanical model of atom to understand the properties of electron in an atom. According to this, the region of space around the nucleus where the probability of finding the electron is maximum is called an orbital. What is orbital? So the region of space around the nucleus where the probability of finding an electron is maximum is called an orbital. What is orbital? The space where the probability of finding an electron is maximum around the nucleus is called orbital. Next, quantum numbers. Quantum numbers are used to locate the address of electron in the atom. Quantum numbers are used to locate the address of electron in the atom. One more definition. A set of numbers used to provide a complete description of an electron in an atom are called quantum numbers. There are 4 quantum numbers required for a complete explanation of electrons in an atom. They are principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. Let us go through the detailed explanation of these 4 quantum numbers. The first one, principal quantum number. It was proposed by Niels Bohr. It is denoted by small n. The values of n 1, 2, 3, 4, etc. are k, l, m, n respectively. Small n represents main shells or orbit number. Small n represents the main shells or orbit number. So if you take the Bohr's model, in that so different orbits will be present. Each orbit that represents the n. It indicates the size and energy of the orbit. Principal quantum number so indicates about the size and energy of the orbit. The total number of orbitals in an orbit is equal to n square. The total number of orbitals in an orbit is equal to n square. The maximum number of electrons in an atom is equal to 2n square. The maximum number of electrons in an atom is equal to 2n square. Second one, azimuthal quantum number. It was proposed by Sommerfeld. It is denoted by small l. It depends on principal quantum number, that is L values depends on small l value, where L is equal to n minus 1, where L is equal to 0, 1, 2, 3, etc. or n minus 1. The value of L represents various subshells. If L value is 0, the name of the subshell is S and the shape of the orbital is spherical. If L is equal to 1, subshell is P, shape is dumbbell. That means P orbital is having the dumbbell shape. If L value is 2, name of the subshell is D and shape of the orbital is double dumbbell. D orbital shape is double dumbbell. If L value is 3, name of the subshell F, then F shape is complex shape. The total L values for a given N value is N. Then if you observe this table, in this table, main shell N is equal to 1, subshell L is equal to 0. So that means the number of subshells 1. Main shell is N is equal to 2. Subshell L values are 0, 1. 0 in the sense S orbital, 1 in the sense P orbital. Number of subshells 2, that means 2S, 2P orbital. If N value is equal to 3, L value is equal to 0, 1, 2. Subshells are so S, P, D orbitals. Number of subshells are 3, 3S, 3P, 3D orbitals. If N value is equal to 4, subshells L values are 0, 1, 2, 3. That means number of subshells are 4. They are 4S, 4P, 4D and 4F. This azimuthal quantum number indicates the shape of the orbital and angular momentum of electron. And the third one, magnetic quantum number. It was proposed by Lande. It is denoted by small m. Magnetic quantum number depends on azimuthal quantum number. M values are ranging from minus L, 0, plus L. The total M values is equal to 2L plus 1. The total number of M values indicates the total number of orbitals in the subshell. The total number of M values indicates the total number of orbitals in the subshell. If L is equal to 0, then M is also 0. Let us see the table here. Subshell L values and number of orientations M values. Number of orientations in the sense number of the orbitals present in it. If subshell is S subshells L value is 0. So then number of orientations 1, M values 0. If P subshell, that means P orbital L value is equal to 1. Number of the orientations in P orbital, again Px, Py, Pz, 3 orientations are present in this pre-orbital. Number of M values minus 1, 0, plus 1. And coming to the subshell D, L value is 2, number of orientations 5. D orbital is having the 5 orientations, that is dxy, dyz, dxz, dx square y square and dz square, like that 5 orientations. To these 5 orientations M values are minus 2, minus 1, 0, plus 1, plus 2. Next, subshell F, L value is 3, number of orientations 7. M values are minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Magnetic quantum number indicates the orientation of orbital in space. Magnetic quantum number significance is it indicates the orientations of orbitals in space. The number of orbitals in an energy level is equal to n square. As n is equal to 1, only one orientation, that means one orbital will be present. If n is equal to 2, so then 2 square, that means 4 orbitals will be present. So that is 1 s orbital, 3 p orbitals. If n is equal to 3, 9 orbitals will be present, that is 1 s orbital, 3 p orbitals and 5 d orbitals. So similarly, like this we can calculate the orbitals in an energy level. The number of orbitals in a subshell is equal to 2L plus 1. The maximum number of electrons in a subshell is equal to 2 into 2L plus 1. Fourth one, spin quantum number. So it was proposed by Uhlenbeck and Goudsmit. Spin quantum number represented with s, small s, when an electron around the nucleus in orbital, it possesses spin due to the rotation or due to spinning. Electron can have two types of these spins. One is clockwise direction and another one is anti-clockwise direction. Spin of clockwise direction of electron is upward direction. That means the symbol is up headed arrow and its value is plus of. For anti-clockwise direction of an electron is down headed arrow mark and its value is minus half. For each value of m, so there can be two s values. That means for each of the m value, in the sense for each orbital, it is having the two spin values. It indicates the direction of the spin of the electron. It indicates the direction of the spin of the electron. Maximum number of electrons in an orbital is 2. The allowed number of electrons in an orbital is 2. In an orbital, only 2 electrons are allowed. The maximum number of electrons present in S, P, D, F subshells are 2, 6, 10 and 14 respectively. That means S orbital so contains only maximum 2 electrons. P orbitals contains maximum 6 electrons. D orbital contains maximum 10 electrons. F orbital contains a maximum of 14 electrons only. Thank you. Thank you for watching this video.